Okay, today we will continue with our discussions on switched reluctance motors. We understood in the last lecture the following. Number 1, the switched reluctance motor operates because their windings are switched and operates because it works on the principle of variable reluctance, right. This is one, and it has multipole windings in the stator, okay, and no winding in the rotor. Invariably it is a doubly salient machine with saliency both in stator and rotor, unlike in many other conventional machines. In fact, the conventional machines, there is no machine which is doubly salient. If you take a DC machine, it is singly salient because there is saliency in the stator. If a synchronous machine, it can at best have a saliency in the rotor if there are salient pole synchronous machines. Okay. Therefore, this is special, and this is one machine where number of poles in stator and rotor are different. This is the difference. Okay. So, there will be a combination of stator and rotor poles. It could be 8 by 6, it could be 6 by 4, it could be 4 by 2, like this. Okay, they have to be different, and there are pair of coils, okay, which are connected in series. So, if you have a 8 poles in the stator, it will be made as 4 phase. If you have 6 poles in the stator, it will be made as 3 phase. If you have 4 poles, you can make it as 2 phase, right. So, the angle between the successive switching will be the angle between the 2 poles, okay. And here one more thing you notice is we always deal with mechanical angles, we do not deal with electrical angles in this switched reluctance machine, right. Okay. Now, we also discovered that there is energy stored in the air gap, mainly because there is no energy stored in the iron. Why there is no energy stored in the iron? We assume the iron to be infinitely permeable, means for the given flux density there is no H. So, H is 0, though B is non-zero, because flux, what is the energy stored per unit volume is half BH, is not it. So, if you look half BH, so there is no energy in the stator in the iron, all energy in the air gap, and energy in the air gap will be generally told as both a field energy as well as co-energy, W field and W field dash, and because if it is a linear system they will be equal, if the system is non-linear they will not be equal. We also have realized that energy stored will be at any instant will be proportional to half Li square if I is the current flowing in the winding. Invariably we can assume that at one instant only one winding is excited. So, it is half of L of that winding into I square of that winding, okay, neglecting leakage, fringing, etc. And that means the torque that is produced is a space derivative of the energy. Whatever energy, so long it is a virtual work. So, energy changes with space, it will produce the torque, okay. So, it is dW field by d theta is the torque, okay, and dW field is half Li square. So, delta W field by delta theta when I is constant will be half I square dl by d theta, right. So, your torque is proportional to square of the current in the winding. So, it does not matter which direction the current flows, because it is square, number 1. Number 2 is it is proportional to the inductance gradient dl by d theta, how the inductance is varying with theta. So, if either current is 0 or if the inductance gradient is 0, there is no torque, okay. So, now the both of them have to be non-zero. Okay. There must be a current and there must be inductance gradient. If the inductance gradient is 0, no torque. Okay. Now, we also discovered that L, the inductance, is a function of position theta and as well as the current I if there is saturation coming into the picture. Okay. So, this is one factor you need to know. So, in this machine the information on inductance is very critical, right. So, you should know what is actual inductance of each of the coil and its variation with rotor position. So, as you go on moving the rotor, inductance will change. We discovered it will assume a minimum value at what position? Inductance of a coil will minimum value when it is unaligned. Unaligned means bulk of the air gap is in line with the pole axis, unaligned. Okay. Then, so if the rotor pole is totally out of phase with the stator pole, then it is unaligned and therefore, there will be a minimum inductance. And then if you move the rotor and come to aligned position, it will have a aligned inductance, it will be maximum value inductance. Between minimum to maximum variation you can assume to be linear, okay, and sometime it may be non-linear, right. Now, so this gradient is therefore critical. Okay. So, today we will look at these things in little more detail and see how we go about further into the energy conversion process. Okay. So, we have seen that the flux linkage psi or lambda will be a function of current, okay, will be a function of current, and for a fixed current, right, for a fixed current here as shown in this arrow, there will be this is the unaligned inductance L and this will be aligned inductance LU, LA and LU you can say, and for as the theta changes. Okay. Therefore, there is a stored energy or a co-energy will be increasing. Say here this will be the co-energy, here the co-energy will be like this, okay, as you do like, you know, this will be the co-energy, then this will be the co-energy. What you see here is there is an increase in co-energy with theta. So, there will be dW field by d theta, right. How much increase? You know, if you increase, say this is the position, increase by a small angle delta theta, what will be the delta W field dash versus delta theta or divided by delta theta will be the torque. So, there will be a torque at every instant experienced by the shaft, experienced by the rotor, which will be as you just move by an incremental position, how much will be the increase in the co-energy. Is it okay? That is the principle. So, there is a, this is a typical picture of the variation of the inductance with theta, okay, as you go here, right. So, as the rotor rotates, the inductance L varies between two extreme values, okay. This is obvious, we have already mentioned. Minimum is LU unaligned and that is here, and maximum is LA which is aligned, okay. So, if you neglect fringing, now if you neglect fringing, it results in sharply defined corners which coincide with particular positions. See, you can assume that the flux is very much going like in a tube, okay, not straying out from the tube. So, the flux tubes, if you say it is just nicely flowing in the stator core and then nicely enters the rotor core, okay, in a more or less straight path without fringing. Okay. Now, the upper and lower corners occur when rotor and stator pole corners are in line, okay, and between these positions inductance varies linearly, okay, that is what we have said. Okay. As the overlap area varies, we assume that it is like a geometry, from minimum value to maximum value we assume it varies linearly. Okay. So, what we are trying to say is, here is the rotor pole R and here is the stator pole S, okay, and beta S is the angle of the stator pole and beta R is the angle of the rotor pole, okay. Now, in this case we are assuming beta S equal to beta R, right. In this case what will happen is, let us say at this is unaligned position, is not it. Unaligned position means this whole of the air gap here is fully in line with the pole, okay. This air gap is, and then from unaligned it goes to aligned here, okay, and that means the beta S and beta R are same, the whole stator pole is fully in line with the rotor pole. So, a change from here to here. So, supposing I plot this unaligned to aligned, you know, then the variation you assume to be unaligned is LU, aligned is LA. So, the variation you are assuming to be linear, is not it, linearly changing with beta S. This angle is beta S, is not it, this angle to this angle, right. I mean this scale is much larger than this scale, okay. It is not just same one to one. So, this is the variation of the inductance variation from unaligned to aligned, okay. Now, this is a positive gradient of inductance, then it will go back to negative, it will go through a cycle now, the variation in space. Any doubt on this up to here, okay, right. So, you can express this L as a function of theta will be unaligned to this the NP square, a number of you know this L is n square into reluctance, isn't it? Permeance, n square into permeance is the L, isn't it. So, permeance is A mu by L, I mean, isn't it. What is permeance? Is reverse of reluctance, permeance 1 over reluctance, reluctance L over A mu, okay. Here is mu naught. So, you have mu naught here R1 into L alpha, that is how much you have moved, okay, divide by this is L is in all the cases it is the G, etc., okay. You can just check this. So, we are assuming a linear variation, okay. So, there will be one reluctance at minimum value, another reluctance at maximum value, okay. Now, if the rotor and stator pole arcs are different, see till now what we assume that pole arc of stator rotor are same, beta S is equal to beta R, okay. Now, if they are different, what will happen, okay, then there will be a dwell at maximum inductance. So, there will be over some positions at maximum inductance where it will, even if you move, there is no variation in inductance, is not it, okay. So, how will it look like? Now, if the rotor is larger than the stator, as you move there are some positions in which this beta is, you can say is the, you know, if this is the beta is the angle which is half of the difference between the beta R and beta S. Now, there is a twice this is gamma, okay. So, there is a dwell here as it varies, is it clear? Because it will not be if it is same then there will be linear, otherwise it will be linear, but then it will not vary at all. At small angle it will not vary. I think this is a simple concept of geometry, okay. It does not vary if this because this angle is not the same as this, okay. This is called a dwell at maximum inductance, okay, that is a constant at maximum inductance, right. Now, other way around, if the interpolar arc of the rotor exceeds the stator pole arc, that means interpolar arc is more, then you find a dwell at minimum inductance. See, this is dwell at maximum inductance, otherwise it dwell at minimum inductance, because your interpolar arc is more. So, there will be some parts in which even as you move there will be no variation in geometry. As you move the rotor, there is no variation in geometry at the air gap. So, you find that zeta, okay, then there will be a dwell here, okay, because your interpolar angle is more than the pole arc of the stator, okay, interpolar arc is more than this. So, this is zeta, which is half of the difference between interpolar arc minus this, okay. Therefore, you find there is a constant inductance even when you vary. Any doubt on this? I hope it is obvious. Okay. One time we say we have taken 3 cases. One is the pole arc of stator rotor same, another is they are different. Okay. So, the rotor is more, then there is a dwell in the maximum inductance. If the interpolar arc is more, there is a dwell at the minimum inductance. Okay.
Whenever we are having difference between PS and DR, we get dwell at both ends. Minimum also and maximum also we are getting.
Yeah, maybe it is yeah, that is likely to happen, right. But it depends upon the geometry. But can you not have, for example, if there is a the number of stator and rotor poles are not same. Okay. So, number of stator rotor poles are not same, you can still have a same beta s beta r, but interpolar may be more, right. Okay. Now, we have defined these terms when geometric constraints, that gamma is beta r minus beta s by 2 and zeta is pi by n r minus beta r plus beta s by 2. It is geometric, simple geometric expressions. Okay. Okay, one is interpolar overlaps and another is polar overlaps. Okay. Now, okay, now let us say there is some animation our people have done. Let us hope it. See, you are moving, and now how the inductance is changing, right. There is beta s beta r, okay. Is it getting clear? I hope it repeats. It is repeating, so you can be okay. So, you can see how the inductance is varying. There is a dwell, okay, at both sides there is a dwell, maximum minimum there is a dwell, okay. So, you find it appears, I hope it is illustrative, right. As you change beta, as you move the now you are moving the stator, it is relative motion basically. So, it is aligned position, you have the maximum, okay, and see now it is aligned. So, it will have a maximum, and then it continues, right. Then it has come to the minimum, and then it has a dwell here, and after it touches this point again it will be reluctance will go on changing. Okay. So, you have a variation like this. So, rotor position information is used to control the. Now, the point is you must, what time you must inject a current in the winding. Current you must inject in such a instant where there is a positive gradient of inductance, only then you get a good torque. Okay. If you pass a current when it is negative gradient, it will not give you a positive torque, it will give a negative torque, or if you give it at 0, then it will give a 0 torque. Therefore, rotor position sensing incidentally is very critical in this machine, right. Information used to control the phase energization. So, what phase to be energized, okay. Even a wrong phase energization also may create problems, okay. So, you can this is one of the factors you need to know. Rotor position information is used to control phase energization in optimal way to achieve smooth continuous torque and high efficiency, okay. So, the conduction angle for phase current, how much, see you pass a current, but how long you maintain the current, it should not allow fully, because you should wait. What will happen is you have to pass a current through say one phase, okay, and then it will continue till there is a positive inductance gradient, but then after some time it should collapse. Okay. So, there is a conduction, there is an angle of conduction, how much time it will be there for this. Okay. Ideally, you would like to have a rectangular type of current in the winding, rectangular type, is not it? But is it possible to pass a current, a constant current in the winding? It may be, it may not be impossible, but it is involved. If you, all you can apply is a constant voltage, is not it? To a winding you can apply a constant voltage through, maybe through a battery or through a rectifier. Okay. When once you have a constant voltage, but current will be is a dynamic circuit process, is not it? It will be LdI by dt and all the things are there. Okay. So, conduction angle for phase currents of stator is controlled and synchronized with the rotor position, usually by means of short position sensor. Okay. You sense the position and do this. So, you do some signal processing. Okay. Nowadays there are tools available for you. Okay. Now how you can just see here at what time which winding has to be energized. Okay. And there may be overlap also. Many times what happens is you push a current in second winding, but first current has not yet died down also. There may be because of the circuit inductances, etc. Are you making sense after what it is doing? Okay. How when there is a, when it is going through inductance gradient, how the appropriate windings are getting energized. See the it is moving like, and then it is aligned. Now it is, this is winding is energized. Okay. Then this has to move. So, this winding has to be energized, okay, to produce a torque here. Okay. Then this winding has to be energized to push it further. Okay. Right. Now, this winding is energized because it has to push it further. Okay. There could be overlaps, that is what now when once it aligns, then that winding need not be should not be energized when it is aligned. Okay. Wait. Then this one is getting energized. Okay. Is it clear how the windings are energized? You see how they are energized in cyclical manner, different coils are energized. Now, point is, this is one set of coils which are there, this is another set of coils. Okay. So, they are getting energized, right. Any doubt on this, because this is very important, how the different coils are energized. So, your controller must be able to take care of energizing the appropriate coils at appropriate instants after sensing the rotor position. Okay. So, you will see the continuously torque rotor is experiencing a torque and causing a motion. Okay. And how much, so what is the speed in which it operates will depend upon how you switch, sequence of switching, and how much torque it will give depend upon how much current you pass and how much is the inductance gradient, etc. Okay. So, I think we have the I hope a more clearer picture now of the way of energizing the different coils. Okay. Right. Any doubt on this? You are sure that it is switching the right coils at right instants, or any doubt? Yeah.
So, we are switching two coils at a time.
No, one is switching out, the point is what is, see you for example, you switch in a coil, let us say this coil is switched and it will take time for it to go down. You see now this is switch coil, this is coil, now it has switched off. So, there is a overlap times will be there. Okay. So, at any time according to this two coils get See now this coil and this coil is energized, okay, but then you look at how they are. See now this is has to carry full current, but this has to be almost shading almost fading out the current here, okay. Now it has to see, the point is there you can't show the, see it has already switched off, right. So current will be more like a pulses, it will rise, it is not that instantly it will go to the position, okay. So there may be overlap times, but second one current may be going down already, because there will be always be in all the this for how the switching is done in all this. How do you think the switching has to be done? You put somebody laborer on the job to go on doing switching, huh? So it should be some power electronic switches, IGBT, MOSFETs, etc. And they have their own times of switch on, switch off also, and you also have a freewheeling system, isn't it? So there will be it will not be abrupt, because if you have a sudden di by dt, it will have its own problem of surges, okay, right. Okay, now we will we can see now that, look at the position now, you are passing a ideal current, this is the ideal current, ideally you want a rectangular block of current, okay, I flowing in the winding, right, and because it is this range where you have a positive inductance gradient, okay. So you are very happy because your dl by d theta is positive and I is positive. So I square dl by d theta will give you a nice torque here, there will be a positive torque from here to here, okay. Is it clear? And then this is for this coil, of course then you repeat it after the next coil, etc. But this is a motoring situation. Supposing you energize a coil here, where it is coming down, I square dl by d theta now is negative, because inductance is gradient is negative, okay. So you have this, therefore this will be a braking situation here, okay. This is braking, this is motoring, is it clear? Okay, how we get the braking and motoring situation, okay. So what we mean is a positive torque is produced at angles when the inductance gradient is positive, and current waveforms are superposed on the angular unsaturated phase inductance. Ideal current wave. So the ideal motoring current is a rectangular with rising inductance, ideal braking current is a rectangular with falling inductance. We are repeating the same thing, okay. So current must be switched on and off in synchronism with the rotor position, right. So you must switch on at the right position when the inductance is just about to rise, and switch off at the right position when inductance is just about to fall, okay. And therefore SRM is a shaft position switched machine. So it should be switched based on the position of the shaft or the position of the rotor, okay. So it is like a square wave brushless DC motor. After all, what is a commutator? A normal DC commutator is also like a mechanical switch. It also does switching of each of the windings inside the armature at appropriate positions, okay, as it goes into the pole axis or interpolar axis, okay. And this is also being done like that only. So you are in fact you are creating a rotating magnetic field by continuously switching the stator coils. What are you doing? You are rotating, you are creating rotating magnetic field by switching the coils, okay, not by 3 phase windings, 3 phase currents. So this is also another way of producing a rotating magnetic field, okay. So practically the current waveforms at high speed, but what happens is the current waveform is not that ideal. It depends upon the speed also, because there is also a back EMF, there is a speed voltage also generated in the coils. How will the current rise or fall? There will be, you have an equation, voltage equation, V equal to Ri plus d lambda by dt, is not it? What is lambda? Lambda is a function of L and I, okay. It will be L di by dt plus I dl by d theta, or I dl by dt, which is I, okay. So, there will be a voltage in the coil due to the change of current, there will also be a voltage in the coil due to the change of speed, due to the change of position, isn't it? So, the one you are aware of speed voltage as well as transformer voltage, okay, both will be there. So, the current response will be decided by this circuit equation, that you are applied a constant voltage V equal to Ri plus d lambda by dt, where lambda is Li, okay. So, you have to try to find out you must solve this differential equation, and your theta is changing with time, right, and L is changing, okay. So, therefore, there will be the what are self EMF in the motor, okay, and this, therefore, there will be some. So, since the currents are all pulsed currents, not constant rectangular current, there will be ripples in the torque, because your I square is not a fixed, they will be changing with time, okay. So, what you notice here is, if this is the variation of inductance, okay, if this is the variation of inductance, the current waveforms, you in fact invariably they switch little earlier, than this, switched earlier than it goes to positive gradient, okay. So, that is why there is overlap, etc. So, it, and then as you switch on the voltage, it will rise, is not it? In a RL circuit there will be a normal rise in current, but here it is not only RL circuit, it is RL theta circuit. So, there will also be a back EMF problem. So, it will just rise, and then if you switch off, okay, then there may be some freewheeling action, and there may be. So, this is how it will die down. So, you will see starting point of current is here and ending point of current is here, okay. So, you will notice that this is a practical current, okay, and of course, this can be the current for braking. So, therefore, these are the issues that we have to be concerned with, okay. Now, if you have a two phase, this is one case of two phase inductance profiles, I mean there are two windings, say winding 1, winding 2. Now, there will be there are no overlaps, that means winding 1 closes and winding 2 picks up, okay, inductance, but there could also be overlap, say even winding 1 goes to peak, but winding 2 has already started earlier. So, this is the overlap period. So, this is two phase inductance, there will be overlap of the gradients also, right. Okay, this is a 6x4 machine. You have a typical winding, this is the winding of 1, winding of inductance of 1, inductance of 2, inductance of 3, and they will be displaced by the appropriate angles, right. These are, because 6x4 means there are 3 phases windings, okay. Now, what will be the current you would like to push? You would like to push I1 in 1, okay, till it is the gradient, okay, and you want to switch it off here, right. Then when the second one, this will be I2 here, end here, and I3 is when this at this position when it is gradient. So, I3 again ideal. So, ideal waveforms without overlap, okay. So, there will be a torque ripples will be there, Now, with overlap what happens is there is an I1 here, okay. Then I2 has started here, okay. There is an I2 here, okay, and then I3 here, okay. So, there will be these are the overlap periods where both the windings will be carrying the currents, okay. So, there may be reduced torque ripples here from this. So, therefore, a small amount of overlap in excitation current is desirable to minimize torque ripples in the form of notches in the instantaneous torque waveform at commutation instant. Okay. So, what is done is you have to think of or optimizing a situation of switching the currents in the respective windings and also calculate the torque and then find out the to minimize the torque ripples, because unlike all other machines you can have a induction machine which gives a constant torque continuously, you are happy. Here it is like you are just pushing torque like this in pulses. So, that is the problem of switched reluctance motors, because you are just banging the torque. So, shaft is getting a pulsed torques in this. Now, of course, there is also a problem of overlap. There is some advantage, but it should not be too much overlap also, okay. There will be a commutation issues are there. Now, there is also a underlap. Commutation underlap is permissible only at speeds high enough so that the rotor inertia can maintain a rotation through torque notches. See, the thing is there may be possibility where you do not excite any windings, okay. That would mean although developed torque is 0, there is enough inertial torque in the machine, so it produces the necessary sort of a filtering or smoothing, okay. So, now it is the electromechanical system where inductance will smooth the ripples in the currents, the inertia may smooth the ripples in the torque, right. So, you can think of so you can have a rest period to so that the torque 0 torque is developed, but still there is a machine moves with its own inertia. So, underlap at 0 speed may result. Now, one thing is if you have an underlap at 0 speed, then you have a problem, it will not pick up the torque at all, okay. And sometimes it may also lock in, right. So, you may have a problem of starting the motors if there is underlap, okay. Overlap and underlap. Overlap means the two currents will be overlapping between them, but underlap is there is a gap between I1 and I2. That's what the term is used, though it is not a very popular term. I was also not very comfortable to call it as underlap, okay. We could have had a better term, I thought, but some scientists will suddenly use a word, okay. In stepper motors you have used castellated windings, okay, castellated stepper motors, and initially I was not come because the tooth looks like the boundary of a castle, of the medieval castle. So, okay. So, like earlier in Roman type there were castles were there where there were for the sentries to sit, there would be a, in fact you will see them maybe in Delhi also, the old forts, okay. So, earlier they were all living in the castles, most of the rulers, and for the common people to mend for themselves outside, okay. Now, these are the some of the factors which you may be interested. Okay. So, this is what he calls underlap. So, there is a I1 I2, there is a gap here, and I2 I3 there is a gap here, is not it, okay. So, we will I think this is the inductance profile of 6/4 with this type of underlap, okay. Now, not all SR motors admit the same degree of overlap between phases, okay, and these are some of the information that in 6/4 machine minimum conduction angle is 30 degrees and maximum could be 30 to 45 degrees. Conduction angle is the angle in which the current is flowing in the winding, okay, right, and 8 by 6 it could be 15 to 30 degrees, okay, depends upon the geometry, etc. Okay. Now, practical current waves and to have reduced torque ripples. So, what you do is you have certain controllers like hysteresis band, like that hysteresis band. So, you see the current can be passed as one single pulse, or it can be passed as almost a chop it in a way, okay. So, this is one of the ways your current builds up and then it is made to have a sawtooth type of a thing, okay, and then it dies down. So, you will see it starts here and ends here, and there is a overlap here. That means, the second winding has already started before the first winding has died down, okay. So, this will be go like this. So, it will be this will be the current I 1 and this will be the current I 2 and this will be the current I 3, and you will clearly see there is a overlap here, is not it, between the two currents, okay. So, practical current waves I 2 starts before I 1 decays, right. And of course, the speed of the motor also will have an impact on the current response, because it will create a back EMF, is not it. Therefore, for the same voltage, the current responses will be different for different speeds, okay. Now, this will be with a high speed, there will be a, when the speed is high means there will be something to more opposing voltage will be there. So, current will be less, is not it. If your speed is low, okay, then current will be more. So, this will be the response of currents practical waveform for different rotor speeds, okay. Now, so this is one higher speed and lower speed, okay, because of the for the same supply voltage, because back EMF is different. So, this effect causes the torque to fall off at high speed, advancing the turn on angle increases the current and torque up to the point where the total conduction angle equals the rotor pole pitch. So, there is a the switching is important, okay. Now, at low speeds the current can be forced to have rectangular shape by PWM. At high speed the current waveform takes natural shape determined by the speed. At high speeds you have single pulses, at low speeds you can have a chopped ones. Speed at which the current waveform is flat topped is called natural speed. So, that means what is the natural speed? At which the current waveform is flat topped, okay, that is the natural speed. So, this is the natural speed. So, what is the speed of the machine will be? It will be V minus IR over I dl by d theta, okay, and because omega dl by d theta is the, so there is no the transformer EMF term, etc. Okay. So, we will have we stop here and we will have the next lecture.